One light year sounds like a simple number, but it represents one of the most brutal journeys a human being could ever attempt. The hard part isn't just speed, it's everything speed brings with it. Forces the human body was never built to handle. A ship that must survive conditions no engineering has ever faced. And every single problem gets worse the longer the journey continues. Let's start with the number itself. 1 light year is 5.88 trillion miles. That's the distance light travels in a single year, moving at 186,000 miles per second. Nothing in nature moves faster, not particles, not energy, not information. That speed isn't a record waiting to be broken. It's a hard boundary written into the structure of the universe at the moment of its creation. And it is held at every scale we've ever tested. So 1 light year is the distance you'd cover traveling at the absolute maximum speed the universe permits, sustained for an entire year without stopping. That's the scale before we've even climbed aboard. Most people picture the solar system ending just beyond Neptune, which orbits about 30 astronomical units from the Sun. But the solar system doesn't end there, not even close. Beyond Neptune lies the Kuiper Belt, a ring of icy objects extending from about 30 to 50 astronomical units. Pluto is a Kuiper Belt object. Beyond that is the scattered disk, stretching to several hundred astronomical units. And further still, the Oort cloud. The Oort cloud is a vast, roughly spherical shell of icy bodies surrounding the entire solar system. Its inner edge begins somewhere around 2,000 astronomical units from the Sun. Its outer edge extends to perhaps 100,000 astronomical units. This is where long-period comets come from. Bodies with orbital periods of hundreds of thousands or millions of years, perturbed by passing stars and sent tumbling inward on elongated orbits. 1 light year equals 63,241 astronomical units. That places the outer edge of the Oort cloud at roughly 1 light year from the Sun. The solar system doesn't end at Neptune. Its gravitational reach extends to approximately 1 light year. The first light year of any interstellar journey is, in a very real physical sense, the crossing of our own solar system's outermost territory. You wouldn't arrive somewhere new. You'd arrive at the boundary between our Sun's domain and the true void. At the outer edge of the Oort cloud, looking back, the Sun is still the brightest object in the sky, still identifiable, still gravitationally dominant, but 63,000 times more distant than Earth is from the Sun. A point of light, not a disk. And looking forward, the nearest stellar systems are still more than 3 light years away. That void belongs to no star. If you're going to travel 1 light year, you need to pick a velocity and commit. Your choice of speed changes everything. The journey's duration, the physical dangers, the warping of time, the energy requirements, the radiation exposure, the forces on the hull. The fastest spacecraft humanity has ever built is the Parker Solar Probe. At its peak, during close approach to the Sun, it reaches roughly 430,000 miles per hour. At that speed, you could cross the continental United States in under 2 seconds, and it is nowhere near fast enough. At 430,000 miles per hour, crossing 1 light year takes over 15,000 years. The entire span of recorded human civilization fits inside that travel time and still leaves more than 10,000 years remaining. To cross 1 light year in any time frame a human could survive, you need to travel at a substantial fraction of the speed of light. At 10% of light speed, about 67 million miles per hour, the journey takes 10 years as measured from Earth. At 20%, 5 years. At 50%, 2 years. At 90%, about 13 months. At 99%, just over 12 months. These are the velocities where physics starts getting genuinely strange. You can't simply go from 0 to 10% of light speed in a matter of hours. The forces involved would destroy both the ship and everyone aboard. A sustained acceleration of 1 GE, identical to the pull of gravity at Earth's surface, would be physiologically ideal. It would simulate normal gravity throughout the acceleration phase, keeping bones loaded, the cardiovascular system conditioned, and the crew's vestibular system functioning normally. At 1 GE constant acceleration, reaching 10% of light speed from rest takes about 35 days. Reaching 50% takes about 201 days. Reaching 90% takes about 730 days. Manageable timescales. The problem is energy. For a hypothetical crewed ship of 1,000 metric tons, conservative for something carrying everything a crew needs for years, sustained 1 GE acceleration for a year requires energy on the order of many times the total annual energy production of Earth. The entire planet's electricity generation for one ship, one acceleration phase. This cost doesn't scale away with better technology. The Lorentz factor requires a specific amount of energy to reach a specific velocity for a given mass. What technology improves is efficiency. How well you convert stored energy to thrust, how much waste heat you generate. Better engineering can approach the theoretical limit. It cannot exceed it. In 1905, Albert Einstein published the special theory of relativity. Among its results was one nobody expected, and that took decades to become fully accepted. Speed affects time. Not metaphorically, physically, measurably. The faster you move through space, the slower time passes for you compared to everything you left behind. This is called time dilation, and it is one of the most verified predictions in all of physics. GPS satellites orbiting Earth at about 8,000 miles per hour experience it. Without corrections for relativistic time dilation, GPS systems would accumulate position errors of several miles per day and become useless within hours. The correction is built into every satellite in the constellation because the effect is real and the equations are precise. Particle accelerators demonstrate it every single day. Moons are unstable subatomic particles with a half-life of about 2.2 microseconds. They're created in the upper atmosphere when cosmic rays strike air molecules at altitudes of about 9 miles. At their velocities, very close to light speed, they should decay long before reaching the ground. They don't. They arrive at Earth's surface in numbers that only make sense if time slowed for them during the journey down. The Lorentz factor predicts exactly how many survive. The prediction matches observation every time. Here's how the numbers work. The Lorentz factor describes how much time slows for a moving object relative to a stationary observer. At everyday speeds, a car, a jet, a rocket to the space station, the factor is so close to 1 that the difference amounts to a few nanoseconds over a lifetime of movement. But as you approach the speed of light, the factor climbs. At 10% of light speed, it's barely above 1.05. At 50%, about 1.15. At 90%, approximately 2.3. For every year you age aboard the ship, 2.3 years pass outside it. At 99%, it jumps to about 7.1. For every 7 years that pass on Earth, you personally live through 1. At 99.9%, the factor reaches approximately 22. For a 1 light-year journey at 99% of light speed, an external observer on Earth measures about 1 year and 13 days for the crossing. But for the crew inside, with the factor at 7.1, they age only about 7 weeks. They launch, cross 5.88 trillion miles of empty interstellar space, arrive at their destination, and have personally experienced about 52 days. Back on Earth, over a year has passed. Families are older. Events have occurred. The world has moved forward at a rate completely independent of what was happening aboard that ship. This isn't approximation. This isn't a thought experiment. It is what the equations predict, what every experimental test at every accessible scale confirms, and what would actually happen. The Lorentz factor is not approximate. When a muon survives its atmospheric journey longer than its half-life should allow, the Lorentz factor predicts exactly how much longer, not approximately, exactly. When atomic clocks are flown on aircraft and compared to clocks left on the ground, the time difference matches the prediction exactly. When particle accelerators measure particles moving at 99.999% of light speed, those particles behave exactly as the Lorentz factor says they should. 9 decades of experimental physics. Theory and measurement agree at every scale and every velocity accessible to experiment. Special relativity is as thoroughly tested as any scientific theory we have. Step inside the ship and consider what the journey actually looks like. Because it is nothing like flying through space in any film you've ever watched. We don't need to speculate. We can calculate it. The first effect is the Doppler shift. When you move toward a light source at a significant fraction of the speed of light, wavelengths compress. Light shifts toward blue, toward violet, and at extreme velocities into ultraviolet. When moving away, wavelengths stretch toward red and into infrared. At 10% of light speed, stars ahead appear slightly bluer than normal. The sky still looks broadly familiar. At 50%, stars ahead that were yellow now look blue-white. Stars that were orange-red now look yellowish. At 90%, the Doppler shift is extreme. Visible light from stars directly ahead has been compressed into ultraviolet frequencies your eyes can't detect. Stars you expected to see have effectively gone dark. What fills the visible spectrum instead is infrared light from cool, dim stars that were near invisible from Earth, now shifted up into wavelengths your eyes can register. The second effect is relativistic aberration. When you start moving at relativistic velocity, stars that were off to the side appear to shift toward the direction of travel. Stars behind you crowd forward. At 50% of light speed, the entire night sky appears compressed toward the forward hemisphere. At 90%, almost all visible stellar content has been swept into a cone spanning about 26 degrees ahead. Stars that should be to your left, right, and behind you, all compressed forward. The sky in every other direction has gone nearly black. At 99%, that cone has narrowed further. Virtually all visible starlight crowds into a tight ring surrounding a single point directly ahead. Behind you, almost complete darkness. Not because nothing is there, but because light from everything in those directions has been bent forward by your velocity. And there's one more effect. The cosmic microwave background, the faint afterglow of the Big Bang, normally spread uniformly across the entire sky at about -455 degrees Fahrenheit, completely invisible in microwave frequencies. Also, blue shifts forward with your velocity. At 99% of light speed, it has been compressed into visible and ultraviolet wavelengths. The forward arc glows with it. Light from no particular star, but from the oldest light in the universe, the relic radiation of the Big Bang itself, made visible by the speed you're traveling. Standing at the forward viewport of a ship crossing 1 light-year at near light speed, what you'd see would be unlike anything any human has ever witnessed. This is one of the most important physical facts about interstellar travel and one of the most commonly misrepresented. Between the stars, there is gas and dust, the interstellar medium. On average, roughly 1 atom per cubic centimeter in typical interstellar regions. Mostly hydrogen, about 10% helium by number, traces of heavier elements, and scattered microscopic dust grains ranging from nanometers to micrometers in size. By any laboratory standard, this is an extreme vacuum. The best vacuum chambers on Earth contain several 100 million atoms per cubic centimeter. Interstellar space has one. It is almost incomprehensibly empty. At low speeds, this thinness is entirely irrelevant. Voyager 1 has been traveling through interstellar space for over a decade. Its instruments still function. One hydrogen atom per cubic centimeter presents no practical problem at 38,000 miles per hour. That changes completely at relativistic velocity. At 10% of light speed, the kinetic energy of a single hydrogen atom striking the bow of your ship is approximately 400 million electron volts, the energy range of high-energy cosmic ray particles. At typical interstellar densities, the bow encounters on the order of several hundred atoms per second per square meter of frontal area. Each collision individually deposits a small amount of energy, but collectively over months and years, those collisions accumulate. They heat the hull material, create radiation damage in molecular bonds, produce secondary particles that propagate deeper into the structure. At 90% of light speed, the situation becomes severe. Each hydrogen atom now carries relative to the ship about 1,200 million electron volts of kinetic energy, the energy range of protons produced by large research synchrotrons. At 99%, energies rise further still. A ship at 90% is flying nose first into a continuous low-flux version of a particle accelerator beam. High-energy protons striking metal can shatter atomic nuclei, producing cascades of secondary particles, neutrons, pions, heavier nuclear fragments, gamma rays that propagate outward through the shielding material. The shielding required to protect a crew at 90% of light speed would need to be substantial. Meters of dense material at the leading edge. Water is among the better practical choices. Hydrogen nuclei absorb high-energy particle energy more efficiently without generating as many damaging secondary particles as metals like aluminum or iron. But meters of water is a very large amount of mass. And mass, as we'll keep returning to, is the central problem. The energy required to move mass to relativistic speeds is one of the most consistently underestimated facts about interstellar travel. At everyday velocities, kinetic energy scales as 1/2 times mass times velocity squared. As you approach the speed of light, the relationship changes fundamentally. The energy required to gain additional velocity grows according to the Lorentz factor, which accelerates toward infinity as velocity approaches light speed. At 50% of light speed, you need energy equivalent to about 15% of the ship's rest mass energy. At 90%, about 130% of rest mass energy. Rest mass energy is what Einstein's equation E equals mc squared describes. The energy equivalent of mass itself. 1 kilogram of mass corresponds to roughly 21 megatons of explosive equivalent. Accelerating 1 kilogram to 90% of light speed requires about 117 times that energy equivalent. For a ship large enough to carry a crew with life support, radiation shielding, food, water, medical supplies, navigation systems, spare parts, the total mass would be at minimum several thousand kilograms. Each kilogram costs roughly that same energy to accelerate. And then you need to decelerate at the destination. Same cost again. The most energetically dense fuel conceivable is antimatter. When a particle of matter meets its antiparticle, they annihilate completely. 100% of their combined mass converts to energy, exactly as E equals mc squared describes. 1 kilogram of antimatter, annihilating with 1 kilogram of ordinary matter, releases about double the rest mass energy of either alone. Nothing in all of physics can match this energy density. It is the theoretical ceiling. And even with perfect antimatter fuel, the mass ratios are punishing. The Tsiolkovsky rocket equation, first published in 1903 and as unforgiving now as it was then, describes the fundamental relationship between propellant mass and the velocity change it produces. For relativistic velocities, the relationship compounds. To accelerate a ship carrying even 1,000 kilograms of useful payload to 90% of light speed and stop it again at the destination, you need far more than 2,000 kilograms of antimatter. Because you have to accelerate the fuel too, and the fuel for the fuel. The rocket equation compounds the way compound interest compounds, except much faster and in the wrong direction for your mass fraction. The result? The vast majority of the ship's mass at launch would be fuel. A small fraction would be the actual payload, the people and the equipment they need to survive. And we cannot produce antimatter in any meaningful quantity. The combined output of all particle accelerators on Earth generates nanograms of antimatter per year. A nanogram is 1/1,000,000th of a gram. An interstellar mission using antimatter fuel would require kilograms, possibly tons. The production gap is roughly 10 orders of magnitude. That is not a gap engineering can bridge with incremental improvements. That requires physics and production capabilities we don't currently have. In the late 1950s and early 1960s, the United States government funded serious engineering work on a propulsion concept based entirely on existing technology, propelling a spacecraft by detonating nuclear bombs directly behind it. A massive shock absorber plate at the aft end would capture the impulse from each explosion. Several explosions per second would accelerate the vehicle. Freeman Dyson, one of the most formidable physicists of the 20th century, calculated trajectories and performance in detail. Project Orion was not fringe science. Large Orion vehicles could theoretically reach several percent of light speed. Not sufficient for interstellar travel, but a real substantial improvement over anything built before or since. The project was ended by the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. Not by physics, by policy. Orion is a data point. It shows the gap between what we can build and what interstellar travel requires is not absolute. Every serious interstellar propulsion concept that has been rigorously evaluated, Orion, Project Daedalus, laser sails, magnetic sails, identifies real physics that could in principle provide meaningful performance. None are ready. None approach the full requirements. But they're all pointing in the same direction. Assume you've solved propulsion. You've accelerated your ship to 90% of light speed. You're crossing 1 light year. You're going to arrive somewhere. And you need to stop. There is no brake that works in deep interstellar space. No air resistance, no runway, no medium to push against in any useful sense. The interstellar medium creates drag so small, it's a navigational correction over years, not a meaningful deceleration force. The only way to slow from 90% of light speed is to fire your engines in the direction of travel. Thrust yourself backward against your motion, and sustain that thrust until velocity drops to something manageable. This consumes the same amount of energy as the acceleration phase. If you carry fuel for both legs, the initial launch mass grows substantially. The fuel for deceleration has to be accelerated during the outbound trip, which requires more fuel to accelerate the deceleration fuel. The rocket equation compounds again. One-way missions have simpler energy budgets, which is part of why serious proposals for early interstellar missions involve one-way voyages. You only pay the acceleration cost once. But one-way means no return. The first humans to leave the solar system permanently, knowing they won't come back. The physics is more tractable, everything else about it is harder. For missions that intend to stop and return, the energy cost is at least 3 to 4 times the one-way acceleration cost. The compounding makes already enormous numbers more enormous. Proposals exist to sidestep parts of this. A massive laser array in the home system could push the ship outbound without the ship carrying propellant for that leg. But deceleration still must happen at the destination. Without a laser array at the other end, the ship carries its own propellant to stop. which adds mass, which the laser has to accelerate. The problem shifts, but doesn't disappear. Physics charges a fee for crossing interstellar distances. The fee is not negotiable. In 1978, the British Interplanetary Society published the Daedalus Study, a 2-year engineering feasibility study for an unmanned interstellar probe targeting Barnard's star, about 6 light-years away. The proposed vehicle would use inertial confinement fusion. Small pellets of deuterium and helium-3 compressed to fusion by electron beams, triggered 50 times per second. The vehicle would reach 12% of light speed. The one-way trip would take about 50 years. The launch mass, around 54,000 metric tons. The helium-3 requirements for the first stage alone would require mining the atmosphere of Jupiter. Not because the designers were being unrealistic, but because the physics requires it. That's how much fuel a fusion drive needs to push 54,000 metric tons to 12% of light speed. The Daedalus study is notable not because it solved the problem, but because it characterized it, showing with rigorous engineering calculation what the requirements actually are. The Breakthrough Starshot initiative, funded in 2016, targeted a different approach entirely. Tiny light sails, propelled by a ground-based laser array to 20% of light speed. The recognition was that the mass problem is the central problem. Make the spacecraft small enough, and the energy requirements drop from impossible to merely extremely difficult. Different proposals, same constraints. The constraints don't change. What changes is how seriously people try to work within them. Set the energy problem aside. Assume it's solved. The ship is moving. Now the human body has its own separate and serious objections. Every system in your body, skeletal, muscular, cardiovascular, neurological, immunological, hormonal, sensory, was shaped by millions of years of evolution in one specific set of conditions. One gravitational field, one atmospheric pressure, one radiation environment. Remove those conditions and biological adaptation begins. But adaptation doesn't mean improvement. It means optimization for the new environment. And the new environment is not the one your biology was built for. Bone. In microgravity, the mechanical stress from standing and walking, the signal that tells bone-building cells to maintain their pace, disappears. Osteoclasts continue breaking bone down at the normal rate. Osteoblast activity slows. Bone density falls at roughly 1 to 2% per month in the most affected regions. Astronauts on 6-month space station missions lose an average of 10 to 15% of their bone mineral density. Recovery takes many months after returning to Earth, and some density loss never fully recovers. Extend that 6 months to the years a 1 light-year journey at 10% of light speed would require, 10 years. And the implications are profound. We might be wrong about the extrapolation. The biology might plateau. But we don't know. And that uncertainty at these distances is a serious problem. Muscle. International Space Station astronauts follow mandatory daily exercise protocols. 2.5 hours of structured resistance training and cardiovascular exercise every single day. Required by mission rules, not optional. And despite that, they still lose up to 20% of muscle mass over a 6-month mission. The exercise slows atrophy. It cannot stop it. The body continuously optimizes toward the actual environment it's in. Over years, that accumulated adaptation deepens into something for which there is no established rehabilitation protocol. Cardiovascular system. In microgravity, there's no upward direction for blood to fight against. Fluid redistributes toward the head and chest. The body senses elevated pressure in the upper body and begins excreting fluid. Blood volume decreases. The heart, no longer working against gravity to reach the brain, adapts over months, becoming somewhat smaller, remodeling toward a less stressful workload. This is the wrong adaptation for a return to gravity. Astronauts returning from 6-month missions frequently need assistance leaving the spacecraft. Blood pressure drops upon standing, people faint. Reconditioning takes weeks of gradual re-exposure. The longest continuous spaceflight on record is 437 days by Russian cosmonaut Valery Polyakov aboard the Mir space station. An interstellar voyage at 10% of light speed takes a decade, more than 8 times longer than the longest anyone has ever spent in microgravity. Vision. About 60% of astronauts who spend extended time aboard the International Space Station report visual changes after their missions. Without gravity pulling fluid toward the feet, more cerebrospinal fluid accumulates around the brain and optic nerves than normal. The elevated pressure can cause swelling of the optic disc and subtly deform the eyeball, shifting focal length. The most common result is a shift toward far-sightedness. Some of this reverses after returning to Earth. Some doesn't. There are astronauts with permanently reduced visual acuity following 6-month missions. Compromised vision on an interstellar ship is not a minor inconvenience. The crew's ability to keep the ship functioning depends on being able to see what they're doing. Immune system. Studies have shown that immune cells exhibit reduced functional capacity in microgravity. Several viruses that healthy immune systems normally keep suppressed show signs of reactivation in astronauts on longer missions. Epstein-Barr virus, varicella-zoster virus, cytomegalovirus. In a small crew living in a closed habitat for years, this immune suppression compounds over time. Any illness encounters immune systems running below their design capacity. Medical care is whatever was brought on the ship. There is no hospital, no specialist, no possibility of evacuation. Every medical event is managed with the training and supplies aboard, with communication delays of months to years for any advice from Earth. The most reliable solution to the microgravity problems is artificial gravity through rotation. A rotating structure creates centripetal acceleration physically indistinguishable from gravity to anyone standing on the inner rim. Bones get the mechanical loading they need. The heart gets the gravitational challenge it evolved to handle. Fluid distribution returns to normal. The engineering challenge. The human vestibular system can tolerate rotation up to about 2 rotations per minute without producing significant disorientation. To produce 1 g of effective gravity at 2 rotations per minute requires a rotating ring with a radius of about 738 feet, approximately the length of 2 football fields end to end. Not physically impossible. Multiple credible engineering studies over several decades have proposed rotating habitats at this scale. But it adds mass. Every structural element of that rotating ring is mass. The propulsion system must accelerate to cruise velocity. The solution to the biology problem imposes additional costs on the energy problem. These challenges are not independent. Solving one makes the other harder. This is the pattern that runs through all of interstellar engineering. The problems interconnect. Every solution has costs. Every cost has consequences. In interstellar space, far from Earth, far from any stellar magnetic field, far from any atmosphere, the radiation environment is constant and arrives from every direction simultaneously. The primary threat is galactic cosmic rays, high-energy particles, predominantly protons, but also heavier atomic nuclei stripped of their electrons, accelerated to near light speed by violent astrophysical events scattered across the galaxy. Supernovae accelerate particles at their expanding shock fronts. Pulsars, with their extraordinarily intense magnetic fields, accelerate particles continuously. Active galactic nuclei contribute particles at the very highest energies. These particles travel through the galaxy for millions of years, losing relatively little energy, arriving at any point in space from every direction, continuously, without pause. On Earth, Two shields handle this. The magnetic field deflects most charged particles, and 60 miles of atmosphere absorbs the secondary particles produced by those that do enter. Your annual radiation exposure from cosmic rays at Earth's surface is roughly 0.3 millisieverts, managed and safe for a human lifetime. In interstellar space, neither shield exists. When a high-energy proton hits an aluminum nucleus, it can shatter it. The resulting shower of secondary particles, neutrons, pions, heavier nuclear fragments, gamma rays, spreads outward from the collision point. In some configurations, a thin aluminum hull actually increases the biological dose inside the spacecraft because one incoming particle becomes many outgoing particles, each capable of causing tissue damage. Hydrogen-rich materials, water, polyethylene, certain hydrogen-containing polymers, absorb high-energy particle energy more efficiently. Water tanks surrounding the crew compartment serve dual purpose: radiation shielding and water storage. But meaningful radiation protection requires meters of material, not centimeters. Astronauts on the International Space Station, partially shielded by Earth's magnetic field, receive 100 to 200 millisieverts per year, roughly 60 to 100 times higher than at Earth's surface. In deep interstellar space without any magnetic field protection, unshielded annual doses would be higher still. Over a decade-long voyage, the cumulative dose is what matters most. The probability of radiation-induced cancer increases with cumulative dose. The math doesn't allow exceptions. High-energy heavy ions, carbon nuclei, iron nuclei, silicon nuclei moving at near light speed, cause physical disruption along particle tracks through brain tissue. Not just diffuse chemical damage from ionization, but actual structural disruption. Axons can be severed. Myelin sheaths can be damaged. Neurons along the track can be physically destroyed in ways the body's normal repair mechanisms cannot simply fix. Animal studies with heavy ions similar to galactic cosmic rays have documented measurable cognitive effects at doses relevant to long-duration spaceflight. Impaired spatial memory, reduced performance on problem-solving tasks, increased anxiety, reduced behavioral flexibility, changes in the ability to learn new tasks. Not subtle population-level statistics, measurable changes in individual animals. The cognitive functions most sensitive to heavy ion radiation are precisely those most needed on an interstellar mission. Complex reasoning, adaptive problem-solving, spatial navigation, decision-making under novel and high-stakes conditions. These are the mental capacities that keep the crew alive. The radiation environment works against those capacities over time. Not as a guarantee, as a growing probability, with every additional year of exposure. At 10% of light speed, a particle with the mass of a single grain of sand, roughly 1 milligram, strikes your hull with kinetic energy equivalent to about 108 kilograms of TNT. That's the actual number. At 20% of light speed, that same grain delivers about 440 kilograms. At 50%, roughly 3,300 kilograms. At relativistic impact velocities, both the projectile and the material it strikes vaporize essentially instantaneously. The kinetic energy converts to heat so rapidly, in timescales measured in femtoseconds, quadrillionths of a second, that matter transitions from solid directly to plasma. The result is a superheated plasma jet expanding outward from the impact point with enormous velocity. Current spacecraft use Whipple shields, a thin outer bumper separated from the main hull by a gap. This works acceptably at velocities of a few miles per second, typical for micrometeorites in the inner solar system. At 10% of light speed, the energies are orders of magnitude higher. More layers, denser leading-edge materials, magnetic deflection of ionized particles, all part of proposed mitigation strategies. None are perfect. Magnetic deflection helps for ionized particles but does nothing for neutral dust grains. Physical shielding is the only countermeasure for neutral material. And every kilogram of physical shielding adds to the mass the propulsion system must push. Engineering for this hazard is not optional. It's fundamental, and it costs mass. You are not following a road. There are no fixed landmarks in any conventional sense. Every reference point is itself in motion. Stars orbit the galactic center. The Sun orbits at about 514,000 miles per hour, completing one circuit in roughly 225 million years. Over the years of an interstellar voyage, surrounding star positions shift measurably relative to where they appeared at departure. Navigation requires knowing where the destination will be when you arrive, not where it appears from Earth now, not where it was when the mission was planned. For nearby stars, we actually have this data. The Gaia mission, a European Space Agency satellite launched in 2013, has measured positions, proper motions, and distances for roughly 1.8 billion stars with extraordinary precision. For absolute position fixing during the voyage, pulsar timing offers the most reliable method available. Millisecond pulsars, neutron stars spinning hundreds of times per second, emitting beams of radio or X-ray emission with extreme regularity, serve as cosmic clocks. Their timing is stable to parts per quadrillion. By measuring the arrival times of signals from several pulsars simultaneously and comparing them to precisely calculated predicted values, a ship can determine its three-dimensional position in the galaxy with high accuracy. Among all the challenges of interstellar travel, navigation is perhaps the most tractable. It is a problem of precision and computation. The physics does not actively work against you the way it does on the energy and biology problems. The degradation of the link to Earth over the course of a 1 light-year voyage changes the fundamental character of the mission. At departure, communications are nearly instantaneous. At 1/10 of a light year, reached in under a year at 10% of light speed, signals take about 5 weeks each way. 10 weeks round trip. This is workable. At 1/4 of a light year, 3 months each way, 6 months round trip. Real-time operational support is functionally impossible. If a system fails and the crew needs guidance, Earth's response arrives 3 months after the request. The crew is operationally on their own. At half a light year, reached after 5 years at 10% of light speed, the delay is 6 months each way, a year for any exchange. News from Earth is a year old when it arrives. This is not communication in any meaningful present tense sense. It is the exchange of records. At 1 light year, signals take a full year in each direction, 2 years for any exchange. A distress call takes a year to reach Earth. Earth's response takes another year to return. 2 years minimum between describing a problem and receiving guidance about it. By then, conditions will have diverged from those described. The guidance may or may not still apply. This is what communication at 1 light year means. Not slow, not delayed, fundamentally different from any form of communication that provides real operational support. The further you go from Earth, the more completely you are on your own. Human beings evolved in social environments. Our psychology is calibrated for a world with other people in it. Remove that environment, and human psychology responds, not catastrophically in every case, but measurably and reliably. Research on isolated and confined environments, Antarctic winter overstations, submarine crews, space station crews, gives a consistent picture. Mood destabilizes over extended isolation. Interpersonal conflicts, which in normal social environments are diffused by the presence of many people and the ability to seek different company, concentrate and intensify in small groups with no exit. Cognitive functions associated with emotional regulation become less effective. Performance on tasks requiring sustained attention degrades. Sleep quality tends to deteriorate when natural light cycles are absent or disrupted. The particular character of interstellar isolation adds dimensions that Antarctic or submarine isolation doesn't have. The communication link doesn't just start limited, it actively worsens. Every month the signal delay grows. Every month what arrives from Earth is older. Consider what communication at 1 light year means for a crew member trying to maintain any relationship with people back home. You send a message. It arrives at Earth a year later. The person you care about reads it and writes back immediately. Their response travels back to you at light speed. It arrives 2 years after you sent your original message. You're reading about what their life was like a year ago, written in response to what your life was like a year before that. The exchange is real. The care is real. The words are genuine. But you are both responding to each other's past selves. The conversation is always conducted in a gap. Any statement you make addresses a situation that has been resolved or evolved long before the response arrives. Any response you receive addresses a version of you that no longer exists in quite the same form. Over years, the correspondence becomes something different from communication. It becomes a form of historical exchange, like writing letters to someone in the past and receiving their replies about your future. Except it is happening in the present tense to both parties. It's just that the present tense for each of you no longer overlaps. Antarctic stations are isolated, but they can call Earth in near real time. Submarine crews are cut off during a patrol, but the patrol ends. The crew of an interstellar ship faces isolation, whose defining feature is not just its duration, but its deepening. Every day, the link is a little more attenuated. Every month, a little more of a historical record than a conversation. Over years, the gap becomes the dominant fact of their relationship to Earth, and the only people who know what it actually feels like are aboard the ship. The energy calculations make one thing relentlessly clear: the extraordinary sensitivity to mass. Every kilogram aboard the ship is a kilogram the propulsion system must accelerate to cruise velocity and then decelerate at the destination. The energy cost per kilogram is fixed by the velocity and the Lorentz factor. It cannot be reduced by clever engineering. The only variable engineering can meaningfully touch is how much mass is aboard. This creates systematic pressure on every design decision. Structural materials are chosen for the highest possible strength-to-mass ratio. Life support systems are designed as compact and light as possible while maintaining reliability. Food and water systems that can recycle and regenerate reduce the mass of consumables that must be carried. But every kilogram of redundancy removed from one system is a kilogram that could allow additional radiation shielding, additional medical supplies, or a fraction more fuel. These are genuine trade-offs, not hypothetical ones. And interstellar vehicles face a situation where resupply from Earth is impossible, which means redundancy must be different in character. Not simply more of the same system, but genuinely different approaches to the same function. So that multiple independent failure modes would have to occur simultaneously to cause catastrophic loss. This philosophy makes each system heavier and more complex than a minimalist design would require. Every engineering choice on an interstellar ship is a negotiation between the cost of failure and the cost of mass. The cost of failure at distances where no help can arrive is absolute. The cost of mass is also absolute. There is no solution that makes the trade-off disappear. There's one more constraint that rarely gets discussed. As you accelerate toward a meaningful fraction of light speed, the kinetic energy your ship carries grows to scales with no terrestrial analog. At 10% of light speed, a 1,000 kilogram spacecraft carries kinetic energy equivalent to roughly 108 megatons. not the fuel, just the motion itself. A failure causing significant structural breakup at cruise velocity doesn't produce wreckage floating in space. It produces fragments, each carrying enormous kinetic energy, continuing on approximately the same trajectory at approximately the same velocity. Designing for graceful degradation rather than catastrophic failure, ensuring that system failures cannot propagate to structural breakup at velocity, is a constraint that doesn't exist for any other form of transportation. A crew member leaves Earth. They have people they care about, a life built over years. They accelerate to 99% of light speed. Their subjective crossing of 1 light year takes about 52 days. During those 52 days, the people they left behind age through over a year. A parent is a year older. A child has grown by a year. Events have occurred, ordinary and extraordinary ones, that the crew member missed. Not because they were distracted, because their relationship to time was physically altered by velocity. When they return, if they return, the gap is real and permanent. There is no way to reverse it, no way to reconcile it, no way for everyone to end up having aged the same amount. They live different quantities of time. The universe recorded the difference with perfect precision. The return trip adds its own layer. Travel 1 light year away at 99% of light speed. Experience 52 days. Stop at the destination. Spend some time there. Accelerate back toward Earth at 99% of light speed. Experience another 52 days. Arrive at Earth approximately 2.5 years after departure, measured in Earth time. You have aged about 110 days. A child you left when they were 10 years old is now 12.5. A parent who was in good health when you launched has experienced more than 2 years of aging. Your physical experience of those 2.5 Earth years is roughly 1 season. The cognitive dissonance of returning to a world that has moved on without you, a world 2.5 years older while you are barely 3.5 months older, is not a simple thing to process. You are the same person. The relationships you had are still real. But the shared timeline has fractured. You experienced a slice of those 2.5 years. Everyone else experienced all of it. The gap is permanent. It can only be acknowledged as the physical consequence of the journey you chose to make. The universe doesn't make exceptions for emotional attachment. It applies the Lorentz factor uniformly, without consideration for what it costs the people on either end. After years of transit, after weeks of subjective time at near light speed, you've crossed 1 light year. You are not at a star system. The nearest stars are still more than 3 light years away. Proxima Centauri, the closest star to our Sun, is at 4.24 light years. 1 light year places you in the interstellar void between our solar system and the nearest stellar neighbors, in the middle of the gap. There is no planet, no moon, no asteroid belt, no atmosphere, no magnetic field providing radiation protection, no solar wind, no meaningful starlight for energy. The sun behind you has shrunk to a bright stellar point. The boundary where the sun's solar wind gives way to the interstellar medium, the heliopause, lies at roughly 100 astronomical units from the sun. You crossed it very early in the journey, in the first fraction of a percent of the total distance. At 1 light year from the sun, the intensity of sunlight has dropped to roughly 14 billionths of what it is at Earth's distance. Solar panels that generate hundreds of watts per square meter in Earth orbit would generate a fraction of a watt per square meter here. Useless for anything practical. Every watt of heat aboard the ship is generated internally. The crew's metabolism, roughly 80 to 100 watts per person at rest. The electronics, the reactor. All of this heat must be managed. In space, the only way to shed heat is through radiation. The radiators of an interstellar ship must be large enough to shed waste heat at a rate that keeps internal temperatures survivable. But radiators are mass. and mass is the central problem. The external temperature of space, defined by the cosmic microwave background radiation, is -455 degrees Fahrenheit, just a few degrees above absolute zero. This actually helps. The huge temperature difference means radiators can shed heat efficiently, even at moderate sizes. But this requires them to have unobstructed views of deep space. Ship geometry becomes a thermal engineering constraint as much as a structural one. And here, at 1 light-year from Earth, isolation reaches its practical limit. A signal takes a year to arrive. A response takes another year. Any news from Earth is over a year old. If something goes wrong right now, there is no rescue that could reach you in any time frame relevant to an emergency. A rescue mission launched immediately upon receiving a distress call would take a minimum of another year just to receive the call. Years more to prepare and travel. You are on your own. The ship, the crew, the knowledge and supplies aboard. Every decision is made by the people present with what they have. There is no one else. Here is something worth recognizing. We are capable of precisely describing a voyage we cannot make. We can state every consequence of crossing 1 light year with quantitative precision. The exact time dilation, the exact radiation dose, the exact Doppler shift, the exact energy cost, the exact rate of bone loss, the exact aberration angle that crowds the universe's light into the forward disk. Which stars would shift into visible wavelengths from the infrared? The exact hue of the compressed cosmic microwave background. None of this knowledge comes from anyone who has made the journey. It has been assembled from 4 centuries of physics, from Galileo's inclined planes to the Large Hadron Collider. From observations of phenomena, the equations predicted before those phenomena were detected. Gravitational waves, black holes, binary pulsar orbital decay. From experimental verification of time dilation in particle accelerators and atomic clock experiments. From satellite operations that depend on relativistic corrections being exactly right. From half a century of human spaceflight data continuously refining understanding of how biology responds to the space environment. All of it assembled into a picture detailed enough to describe in advance what would happen to a crew crossing 1 light year. That's not a small thing. That's science functioning at its best, building knowledge systematically over centuries until it describes phenomena beyond the reach of any individual or any generation to directly observe. The GPS in your pocket depends on relativistic corrections calculated from the same equations that describe a 1 light-year voyage. If those equations were wrong, the GPS would be wrong. It isn't. The muons on Earth's surface are present in exactly the numbers the Lorentz factor predicts. If the prediction were wrong, the muon count wouldn't match. It matches every time. These are not separate coincidences. They're the same physics tested in different circumstances, always returning the same precise answer. The distances between stars are also information. They tell you something about the structure of the universe, about how matter collapses under gravity into stars, how those stars cluster into galaxies, and therefore, how often stars end up near each other versus separated by years of light. The average distance between stars in our region of the Milky Way is about 4 to 5 light years. This reflects the physics of star formation. Stars form from the collapse of molecular gas clouds. Those clouds fragment as they collapse, with each fragment producing a protostar. The typical separation between resulting stars is set by the physical properties of the cloud, its temperature, density, and magnetic field strength. The universe made stars at the scale and density that the physics of cloud collapse produces. Not at human-friendly spacing, not at distances where nearby interstellar travel would be routine. At whatever separation the physics dictated. And the physics dictated separations of light years. The universe is not hostile to life and exploration in any deliberate sense. It is simply structured according to its own physics, which is indifferent to biological requirements or travel convenience. 1 light year, just one, a fraction of even the nearest stellar gap, requires everything we've described. The full gap to Alpha Centauri is 4.24 times that. These are not metaphors for difficulty. They are the actual distances with actual costs attached, governed by actual physics. So what actually happens when you travel 1 light year? Time dilates. The sky transforms. Stars crowded forward into a blazing disk. Colors shifted beyond recognition, the relic radiation of the Big Bang made visible by your speed. The interstellar medium becomes a particle radiation environment, requiring engineering that adds mass and compounds every other cost. Dust grains become hypervelocity projectiles with explosive equivalent kinetic energies. The body loses bone density, muscle mass, cardiovascular conditioning, and possibly some visual acuity and microgravity over years, unless mass-expensive countermeasures are maintained throughout. Cosmic rays accumulate in tissue and brain matter, adding to a statistical ledger of biological risk that never stops growing. Communications with Earth degrade from conversation to correspondence to historical archive, receiving records from a civilization that has moved on while you were traveling. The energy required to accelerate and decelerate a crewed ship exceeds by orders of magnitude the total energy humanity currently produces in a year. And at the end of it, if you've traveled at near light speed, you arrive having aged weeks, while Earth has aged over a year, displaced in time as surely as in space. Every one of these consequences is real. Every one is described by physics, verified at every accessible scale. None of it is speculation. That will change. The history of technological progress is long enough and surprising enough that dismissing future solutions would be premature. The antimatter production problem is not forbidden by physics. It's a scale and efficiency problem. Physics allows antimatter. Physics doesn't restrict how efficiently it can be produced. The rotating habitat for artificial gravity is a structural engineering challenge, not an exotic one. The biology questions about long-duration spaceflight will be answered by long-duration spaceflight. We answer biology questions by going and observing and adapting. What's genuinely unknown is whether there is a solution to the fundamental energy problem that doesn't require inputs that are physically staggering. Not whether better solutions exist, whether solutions that are actually practical at the scale of civilizations, within the constraint of known physics, exist. That's the honest unknown. Not whether humans will ever cross interstellar distances, but when, at what cost, and whether the cost is one any civilization can realistically pay, or one that requires a kind of civilization we cannot yet imagine. And that is how science works at its frontier. Precise about what it knows, honest about what remains open. The civilizations that someday cross 1 light year will build on what we've already understood. They won't discover that time dilates. They'll be managing exactly how it dilates. They won't be surprised by the radiation environment. They'll have solved the shielding. They won't be unprepared for the biology of long-duration spaceflight. They'll have solved artificial gravity and the other countermeasures. They will know what the physics demands because we worked it out here, from the surface of a small planet, with equations and experiments and a willingness to follow the physics wherever it leads, even when it leads somewhere we cannot yet go, even when the honest accounting is humbling. The next time you look up at a clear night sky, at Sirius at 8.6 light years, or Vega at 25, or the idea of Proxima Centauri at 4.24 light years, those numbers aren't just large. They are the measure of what the universe actually is. How much of it there is between the things that shine, how much emptiness separates the points of light. 1 light year of that emptiness, just one, would require a civilization's worth of energy to cross with human beings aboard. And it wouldn't even get you to anyone. It would put you in the middle of the gap, in the cold, particle-thin, radiation-bathed, utterly isolated void between solar systems, with a year of light travel in every direction for any signal you send. On your own, in the fullest possible sense of that phrase. That's what the distance actually is. Not a destination, a demonstration of what the universe is made of, and how much of it there is. And the fact that we can calculate every consequence of that crossing, the exact time the crew ages versus Earth, the exact color shift of the stars, the exact rate of bone loss, the exact energy cost, that's something. That's the product of 4 centuries of people asking precise questions and accepting precise answers. Even when the answers describe a journey none of them could make. Even when the answers are humbling. We know what it costs. We know what it does. We know what it looks like. And that's where every great journey starts. 1 light year sounds like a simple number. But it represents one of the most brutal journeys a human being could ever attempt. The hard part isn't just speed. It's everything speed brings with it. Forces the human body was never built to handle. A ship that must survive conditions no engineering has ever faced.